the James Webb Space Telescope has made a discovery that has left astronomers completely stunned, captured intense, violent bursts of energy surrounding the event horizon of TUN 618, one of the most massive black holes ever observed. These bursts weren't random or mild. They were powerful rhythmic pulses that don't align with any of our current models of black hole behavior. The energy signatures detected by Webb defy what we thought we understood about the way matter behaves near such an enormous black hole. Instead of the relatively even glow that scientists expected from superheated matter spiraling into a black hole of this size, Webb recorded dramatic pulsing patterns of infrared radiation. These bursts were irregular, yet oddly structured, and they seemed to originate from multiple points around TUN 618's event horizon. This behavior is baffling. According to known physics, nothing should escape from the region just beyond a black hole's boundary, much less create such structured and repeating patterns of energy. Activity raises critical questions. Could be causing such anomalies in a black hole that's more than 66 billion times the mass of our Sun? Could this be a sign of unknown physics at play, possibly tied to the long-debated quantum information paradox? There's something entirely unexpected occurring. At the very edge of this cosmic giant, TUN 618 lies at the heart of a quasar, more than 10 billion light-years from, meaning we are observing events that occurred when the universe was still in its early stages. This makes the discovery even more significant. Previously, ground-based telescopes and even the Hubble Space Telescope could only see TUN 618 as a point of light. But with Webb's advanced infrared capabilities, astronomers can now detect detailed structural patterns right near the boundary of the black hole. Patterns that suggest some form of organized, energetic processes taking place where no such activity was thought possible. Dr. Jane Rigby, the Operations Project scientist for the James Webb Space Telescope, noted that these findings reveal aspects of black hole behavior that were invisible to us until now. The specific anomalies detected include infrared pulses occurring every 67 minutes, far too regular to be dismissed as random noise. Even more perplexing are the geometric shapes formed by these energy bursts. They appear to follow patterns or channels that don't align with any known physical structures around black holes. As researchers dug deeper into the data, they uncovered even more astonishing details. The energetic outbursts could suggest that our current models of supermassive black holes are missing key components. Some experts believe this might be the first direct observation of interactions between normal matter and dark energy, something once believed to be beyond the reach of any telescope. If that's the case, these bursts could be the first detectable signs of such interactions. Another theory suggests we may be witnessing entirely new behavior in the black hole's accretion disk. Due to 618's immense mass, the physics operating in its vicinity could be unlike anything we've previously studied. Gravitational forces on this scale might generate shock waves or magnetic disruptions that ripple across the disk in ways we've never imagined. Perhaps the most tantalizing possibility is that these energy bursts are signs of space-time distortions caused by quantum effects, so-called gravity echoes. The ripples might only be visible around black holes of this magnitude, and their detection would represent a groundbreaking moment in theoretical physics. Professor Brian Cox commented on the implications, comparing the discovery to finding a fully formed dinosaur in geological layers that existed before dinosaurs. In other words, TUN 618's very existence combined with its unexpected activity forces us to rethink what we thought we knew, not only about black holes but also about the early universe itself. What makes this discovery so crucial is the unique nature of the event horizon. Boundary is the point of no return, beyond which nothing, not even light, can escape. Observing anything close to, or at this boundary is inherently difficult as we're typically limited to seeing only what happens just outside of. However, Webb's instruments, including its mid-infrared instrument, MII, and near-infrared spectrograph, NIR, SPEC, are capable of detecting incredibly faint heat signatures. The instruments are kept at temperatures just above absolute zero, enabling them to capture data that other telescopes simply miss. When trained on TON 618, Webb revealed a set of radiation patterns no previous telescope had ever seen. The scientific community quickly responded. Institutions around the world are racing to secure telescope time to replicate and confirm these findings. Special conference has already been scheduled at the Max Planck Institute, and theorists are working overtime to revise existing models in light of the new evidence. Though some suggest more conventional explanations may yet be found, the majority agree that TON 618 is showing us something extraordinary. Whether these signals stem from quantum-level interactions or newly discovered cosmic processes, they open a door to understanding phenomena that were previously out of reach. TON 618 isn't just an astronomical curiosity, but be the key to solving some of the biggest mysteries in modern astrophysics. Formed during the cosmic dawn, a period just a few billion years after the Big Bang, that such a massive black hole existed so early in the universe's history already challenges our theories of cosmic formation. If the observed energy bursts, a link to how TON 618 grew so rapidly, they could unlock secrets about the birth of the first galactic structures. Beyond that, these rhythmic signals may help uncover the nature of dark energy, which makes up most of the universe but remains largely unknown. Some theorists even propose that these patterns might offer clues to the black hole information paradox. The debate over whether information falling into a black hole is lost forever or somehow preserved. These discoveries also align with upcoming missions like LISA, the Laser Interferometer Space Antenna, which will detect gravitational waves from massive black holes and might validate what Webb is seeing through different means. At the same time, ground-based observatories like the Extremely Large Telescope will soon provide more detailed follow-ups on TONs 6118. Among the leading hypothesis is that we may be seeing Hawking radiation in action. Although this theoretical phenomenon was predicted by Stephen Hawking decades ago, it has never been directly observed. The bursts detected around TON 618 might be amplified quantum emissions resulting from its immense mass. Another explanation could be large-scale frame dragging, a process where a spinning black hole twists space-time itself. At the size of TON 618, such a force might be creating visible swirling patterns in the surrounding energy fields. Global efforts are now underway to observe TON 618 across multiple wavelengths. The Event Horizon Telescope, which captured the first image of a black hole in 2019, is being prepared to study this black hole within the next few months. Additional data from NASA's Chandra X-ray Observatory and the Very Large Array Radio Telescope will provide complementary insights. Dr. Kip Thorne, a Nobel Prize-winning physicist, emphasized the importance of this discovery, suggesting that Webb's observations of TON 618 might be the most significant advancement in black hole science since the detection of gravitational waves. If confirmed, his findings imply that event horizons are far more dynamic and complex than we ever imagined. It may take up to a year for observational data from various telescopes to align and begin offering a clearer picture. Developing the theoretical models that explain what we're seeing could take several more years, especially if they demand new physics, perhaps even progress in the elusive field of quantum gravity. 608 strange and powerful emissions represent one of the most important black hole discoveries in decades. The data from the James Webb Space Telescope has upended long-standing assumptions about how black holes function at the largest scales. Whether we're seeing evidence of exotic quantum activity, warped spacing, or an entirely unknown phenomenon, it's clear this black hole still holds secrets waiting to be uncovered. These revelations remind us that even with our most advanced technology, the universe continues to surprise and humble us. Tons 618 over 10 billion light-years away connects us with the early universe and offers a glimpse into the hidden workings of reality itself. As we continue to probe deeper into these cosmic mysteries, one thing is certain: our understanding of the universe is far from complete.